Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And this particular video is going to focus on the topic of alcohols and phenols from the WJC Chemistry Unit 4. So it's an A2 topic and we're going to be looking at some of the reactions of alcohols, how we make alcohols, and then we're going to look at the structure of phenol and some of the reactions of phenols as well. And this does have quite a bit of overlap with some of the other topics as well. As always, if you find this video helpful, remember to like, subscribe, share with your friends, and keep checking back for more content. We're going to start off by looking at the oxidation of primary alcohols, so this little title here. And to keep things simple, we're going to use a specific example of ethanol. So ethanol has 2 carbons, 5 hydrogens, 3 attached to this one here, and 2 here. Remember the golden rule that carbon forms 4 bonds, and then an OH group here, which is the alcohol group. Now, if you fully oxidize an ethanol, you end up with ethanoic acid. Now, ethanoic acid still has 2 carbons. It's got a C double bond O, and then the OH group, and then 3 hydrogens here. It's the reaction that will happen in your fridge if you leave a bottle of wine open too long. And what happens is the alcohol, the ethanol that's in your bottle of wine, very slowly will react with the oxygen in the air, turning your wine to vinegar. So you'd start off with ethanol, and unfortunately, if you don't drink your wine quick enough, you end up with ethanoic acid. Now that will happen very slowly at room temperature when there's oxygen present. In the lab, we want to make this happen a little bit quicker. So what we do is we use a reagent called potassium dichromate, K2Cr2O7, and it needs to be acidified. So that's H+, and heated. And you would have excess of the oxidizing agent. Now, if you were asked for the symbols, it would be K2Cr2O7 and H+ in excess. If it asks for the name, you would write acidified potassium dichromate, and then you'd put VI, the Roman numerals for the chromium, to show that it's in the oxidation number of +6. So just be careful. If it does ask for the name, make sure you actually write the name and not just the formula. Now, it's possible to do the reverse of this reaction, to take your ethanoic acid and reduce it back to ethanol. To do this, we use the reagent lithium aluminium hydride, LiAlH4. This needs to be anhydrous, so with no water at all. And the lithium aluminium hydride reduces the carboxylic acid back to the primary alcohol. Now, it is also possible to partially oxidize the ethanol to form ethanal. Now, ethanal has 2 carbons still. That doesn't change. You've got your aldehyde group here, C double bond O, and then a single bond to H, and then 3 hydrogens here as before, and this is partial oxidation. So to do this, you have excess of the alcohol, and then you react it with the K2Cr2O7 and H+, and you distill the product as it forms. and that stops it oxidizing further. So distill the product as it forms. And that'll leave you with just the aldehyde. We call it the partial oxidation. You can do the reverse of this reaction as well. So you can go from the aldehyde back to the primary alcohol. And to do this, you could use the lithium aluminium hydride as for the other reduction, but the more sensible reagent to use is sodium borohydride because it's safer and cheaper. Now, in terms of your exam, if you write lithium aluminium hydride for this reaction, that is absolutely fine. You will get the mark. However, the sodium borohydride will not reduce ethanoic acid down to ethanol. It's not powerful enough. So it's okay to use sodium borohydride for an aldehyde. This is ethanal, by the way. I need to label the name. Ethanal. It's okay to use sodium borohydride for the reduction of an aldehyde. It's not okay to use it for the reduction of a carboxylic acid. And one last thought here is that once you've got your aldehyde, if you decide you need to oxidize it further, you can. And to do that, you use the same conditions as for the full oxidation. So that's the K2 Cr2O7 and H+, and you reflux it or heat it, same thing in this case, and you have excess of these. But it is not possible to reduce ethanoic acid to ethanal in one step, because you have to use lithium aluminium hydride and it'll take it all the way back to the ethanol. So instead what you would do if you had to go from ethanoic acid to ethanol is, let me grab a highlighter pen, you would follow this arrow here, so you would reduce it with the lithium aluminium hydride and then you would oxidize it using the partial oxidation condition. So you'd have to do it in 2 steps. Things are a little bit simpler if we have a secondary alcohol. So the simplest secondary alcohol is propan-2-ol, where you have the OH group on carbon number 2, like so. And if you oxidize propan-2-ol, you end up with propanone. Now propanone still has 3 carbons, but it has a C double bond O on the middle carbon, and then CH3 groups either side. And to do that, we use the same conditions as for the full oxidation on the previous slide. So that would be the H+ and the K2 Cr2O7, which are in excess. And then you heat it or reflux it, either way. And then it's possible to reverse this by doing a reduction reaction, and the safest and simplest reagent is the sodium borohydride reducing agent, NaBH4. However, it is perfectly acceptable to put lithium aluminium hydride here. That's not a problem at all. And you might be wondering why I've not put oxidation of tertiary alcohols in here. Well, tertiary alcohols are resistant to oxidation because it would end up making a carbon with 5 bonds, so we can't oxidize a tertiary alcohol. So we've just looked at different ways of making primary and secondary alcohols, and that is the reduction reaction, either of the carboxylic acid, the reduction of the aldehyde, or the reduction of the ketone. Another way of making an alcohol is by taking a halogenoalkane. So I'm just going to use one example here. I've got 1 bromopropane. So 1 bromopropane. And if you reflux it with sodium hydroxide, NaOH, now the sodium hydroxide has to be aqueous, so dissolved in water. And what happens is the OH group substitutes with the bromine. So you'd end up with propan-1-ol. And the byproduct here would be sodium bromide. Now, bear in mind you could use different halogenoalkanes and so on. This is just an example. The mechanism is really important that we understand this. So I'm going to show you the generic mechanism for how this happens. It's called the nucleophilic substitution reaction. So if you take your, let's just put an R group here to make it easier and quicker to draw out. You've got your carbon to bromine bond here, which is polar, where the carbon is delta positive and the bromine is delta negative. And then along comes your OH minus, which is formed from the sodium hydroxide in water. And what happens is the OH minus is attracted to the delta positive carbon. So you have a curly arrow going from the oxygen to the carbon. This is what we call a bond forming curly arrow. So we're going to form a new bond from the oxygen to the carbon. But this carbon here now has too many bonds, so it breaks this bond to the bromine, like so. It then passes through what's called the transition state. And the transition state shows the carbon to bromine bond breaking. It shows the carbon to oxygen bond forming. The hydrogens and everything else hasn't changed. So the transition state is not something you could isolate in the lab. It's not something you could actually sort of have as a powder or a liquid. It's almost a theoretical thing, but it helps us to understand the mechanism. And we put this funny little symbol at the top right hand corner to show that this is the transition state. And then we draw out the product, which would be R to C to OH. And then put your hydrogens on, and your byproduct, as before, would be sodium bromide. So it's called nucleophilic substitution because we're substituting the OH for the bromine, and the OH minus is acting as a nucleophile. A nucleophile is something that's negatively charged, that's attracted to something positive. So it's something with lots of electrons that wants to be attracted to something positive. It's also possible to go back from the alcohol to the halogenoalkane. So if you have, let's just put a generic alcohol here, R to CH2 to OH. Doesn't really matter which one it is at the moment. And if we want to turn it into the chloroalkane, like so, then you'd use HCl and you'd reflux it, and you'd need a zinc chloride catalyst. Or alternatively, you could use SOCl2, or alternatively you could use PCl5. If you want to make the the bromo version, you'd start with your alcohol as before. And what you'd do is use a mixture 50-50 of potassium bromide and H2SO4. These are not balanced equations or anything like that, they're just to show you what's happening. Overall, and the reagents and conditions that you need. And you'd heat that. And if you want to substitute to make the iodine, you would use a mixture of phosphorus and iodine. which makes Pi3, and then it's the Pi3 that will swap with the OH group, and you'd end up with the iodo version. Okay, so it's possible to go from an alcohol back to the halogenoalkane. Depending on what you want, you'd use one of these sets of reagents and conditions. Okay, we're going to look at our second way of making an ester now, and that's to take your alcohol. So let's take ethanol as the example. So CH3, CH2OH, and you react it with a functional group called an acid chloride. Now, an acid chloride has a C double bond O and then a carbon to chlorine single bond. So it looks very much like the carboxylic acid, except for the OH group has been replaced by a chlorine. So this would be called ethanol, and this is called ethanoyl chloride. And the difference this time is it's not a reversible reaction. You still form your ester group, and this would be the corresponding ester that forms. And the name of this ester would be ethyl ethanoate. And the byproduct for the reaction would be HCl. So the good news here is that it's not reversible. It's a one-way reaction. The downside is the acid chloride here. Now, acid chlorides are quite unstable. You have to make them typically from the carboxylic acid and then react them straight away. So to make this, you would take your ethanoic acid and you'd react it with a reagent called phenol chloride, SOCl2. And that's quite an expensive and nasty reagent to work with. So that's the downside to this reaction, is that you'd have to use phenol chloride to convert the carboxylic acid into the acid chloride, and then the acid chloride can react with the alcohol to form the ester. Okay, in this section we're going to look at the structure and the acidity of a compound called phenol. Now, phenol is a benzene ring with an OH group attached to it. So you could call this hydroxybenzene, but it's actually called phenol. And phenol is far more reactive than benzene is. If you remember back to how benzene reacts, it reacts by electrophilic substitution, where the pi cloud is attracted to an electrophile like this. Now, if you think about the oxygen on the phenol group, it's got a lone pair of electrons, and what it does is it pushes its electrons in towards the pi cloud, and thus it makes this pi cloud even bigger. There's more electrons in it, and therefore it makes it more reactive. So phenol is far more reactive than benzene because of the lone pair of electrons on the oxygen that are pushed in towards the pi cloud, making the pi cloud more electron rich. Phenol is a weak acid. So phenol, when it's in solution, is in equilibrium with the phenoxide ion, which is shown here, and H+. So it's a weak acid. It only partially dissociates. And because it's a weak acid, it will react with sodium hydroxide, which is a strong base, to form this phenoxide ion. But it won't react with sodium carbonate, which is a weak base. No reaction, because it's not a strong enough acid to do that. Okay, so that's how you could perhaps prove the acidity of phenol. It'll react with sodium hydroxide. It will not react with sodium carbonate. So we're just going to look at a couple of reactions of phenol to finish. The first one is making esters. So if you take your phenol and you react it with the acid chloride that we discussed previously, so for instance ethanoyl chloride, you can see with the way I've lined these up that you'd kick out a molecule of HCl, and then you'd form the corresponding ester. So that's the first reaction of phenol, is to make an ester. The second reaction of phenol is to react it with bromine water. So you take your phenol and you react it with bromine. You actually need 3 equivalents of bromine for this. And what happens is substitution. So the bromine substitute into the benzene ring, and it happens in the 2, 4 and 6 position here. So the product that you get is called 2, 4, 6 tribromo-phenol. And the byproduct would be 3 lots of HBr. Now you might be wondering several things here. If you think back to benzene chemistry, benzene doesn't react with bromine water, whereas phenol does react with bromine water. And the reason we've just previously discussed is phenol is more reactive due to the lone pair of electrons on the oxygen that sort of help the pi cloud to like swell up. So this will not happen for benzene. It's not reactive enough, but it will happen for phenol. What would you see as this reaction goes on? You need to know the observation. There are 2 observations. The first one is that you'd see a white precipitate, and the white precipitate is this 2,4,6 tribromo-phenol. And secondly, you would see the decolorization of the bromine water. So if you think of bromine water, it's got that orangey brown color. When it reacts with the phenol, it gets used up to form this 2,4,6 tribromo-phenol, and therefore the decolorization occurs. So it will go from sort of an orangey brown color through to colorless. And then lastly, the final test for phenol is to use iron chloride, FeCl3, and what happens is you get a violet solution produced. You don't need to know why, but the reason that this happens is the phenol, if you can picture this, let me try and draw it out. Really poor phenol ring there. The phenol, the OH group there, has this lone pair of electrons on the oxygen, and what it can do is it can form a coordinate bond to the iron, and it effectively acts as a ligand. Now if you remember back to your D block chemistry, the introduction of a ligand splits the d orbitals into 2 different energy states, higher and lower, so you get d to d transitions, and hence it appears coloured and you get this violet solution. So that's a good test for phenol, is to use iron chloride. Anyway, that was it doesn't feel like it, but a rather quick summary of the alcohols and phenols topic. I hope it was helpful. If it was, remember to like, subscribe, Keep checking back for more content, and I'll see you next time. Thanks, everyone.